Hey everyone, welcome back to the channel. Today, we're going through some challenging but essential questions from Physical Quantities and Measurements, one of the foundations of physics. Before solving these problems, don't forget to watch the lesson video first, link above. Let's dive right in. First question. A physicist measures the mass of an object 3 times, 1.253, 1.255, and 1.254 kilograms. The true mass is 1.750 kilograms. These measurements are precise because they're very close to each other. But they're not accurate since they're far from the true value. So the conclusion is precise but not accurate. Next, question 2. The radius of a circle is given as 2.50 plus or minus 0.02 meters. To find the area, we use the formula A equals pi r squared. That gives us pi times 2.50 squared, which is about 19.63 square meters. The percentage uncertainty in the radius is 0.02 divided by 2.50, that's 0.8%. Since the area depends on r squared, the total uncertainty doubles to 1.6%. So the area is 19.63 plus or minus 0.31 square meters. Now, question 3. What exactly is a physical quantity? It's any property that can be measured and expressed with a unit. For example, time and mass are base quantities, while velocity and energy are derived quantities because they're combinations of the base ones. Question 4. We're asked for the dimensional formula of force. From the equation F equals m times a, the dimension of mass is m, and acceleration is Lt to the power of minus 2. Multiplying gives M⁰L⁰T to the power of minus 2. That's the dimensional formula for force. Moving on to question 5. We need to check whether v squared equals u squared plus 2as is dimensionally consistent. Velocity has the dimension Lt to the power of minus 1, so v squared and u squared both have L squared t to the power of minus 2. Acceleration times displacement also gives L squared t to the power of minus 2. Since both sides have the same dimension, the equation is dimensionally consistent. Question 6. Let's convert 36 kilometers per hour into meters per second. We know that 1 kilometer equals 1,000 meters and 1 hour equals 3,600 seconds. So we multiply 36 by 1,000 and divide by 3,600. That gives 10 meters per second. In scientific form, that's 1.0 times 10 to the power of 1 meters per second. Question 7. How many significant figures are in 0.004560 meters? The leading zeros don't count. The significant digits are 4, 5, 6, and the final 0 after the 6. So, there are 4 significant figures in total. Question 8. Now, the mass of a cube is given as 125.0 plus or minus 0.1 grams, and each side is 5.00 plus or minus 0.01 centimeters. We need the percentage uncertainty in density. Since density equals mass divided by side cubed, the fractional uncertainty is the uncertainty in mass plus 3 times the uncertainty in side. That's 0.08% from the mass plus 0.6% from the sides, giving a total of about 0.68%. Question 9. Which of the following quantities are dimensionless strain, angle, refractive index, or energy? Strain is a ratio of lengths, so it's dimensionless. Angle in radians is also a ratio, so it's dimensionless. Refractive index compares 2 speeds, so it's dimensionless too. Energy, however, has dimensions M⁰L⁰T to the power of minus 2, so it's not dimensionless. Question 10. A student says that 1 Newton equals 1 kilogram meter per second. There's a small mistake here. They missed 1 power of time. The correct unit is kilogram meter per second squared. Question 11. Let's check whether the formula T equals 2 pi times the square root of L over G is dimensionally correct. Acceleration due to gravity, G, has dimensions LT to the power of minus 2. So L divided by G gives T squared. The square root of T squared is T. The 2 pi in front is just a number, so it doesn't change anything. That means both sides represent time and the formula is dimensionally valid. Question 12. Now for the dimensions and SI unit of power. Power is energy per time, or joule per second, also known as the watt. Energy has dimensions, M⁰L⁰T to the power of minus 2. Divide by time, and you get M⁰L⁰T to the power of minus 3. Question 13. If a quantity has dimensions m to the 0, L to the 0, and T to the 0, that means it's dimensionless, a pure number or a ratio, like refractive index or strain. Question 14. The value of G is 9.80665 meters per second squared. If we round that to 3 significant figures, it becomes 9.81 meters per second squared. Question 15. An ammeter reads 2.50 amps with an uncertainty of plus or minus 0.05 amps. We can write this properly as I equals 2.50 plus or minus 0.05 amps. That represents about 2% uncertainty. Question 16. Why can't we add 5 meters and 3 seconds? Because they represent completely different physical dimensions. Meters measure length, and seconds measure time. Only quantities of the same kind, like 2 lengths or 2 times, can be added or subtracted. Question 17. A car travels 120 kilometers in 2.00 hours. Speed equals distance divided by time, so that's 60.0 kilometers per hour. If we convert that to meters per second, we multiply by 1,000 and divide by 3,600, giving 16.7 meters per second with 3 significant figures. Question 18. Now, the dimensions of Planck's constant, h. From the equation E equals h times nu, we know energy has dimensions M⁰L⁰T to the power of minus 2, and frequency has T to the power of minus 1. So, h equals energy divided by frequency, which gives M⁰L⁰T to the power of minus 1. Question 19. A derived unit of kilogram meter to the power of minus 1 second to the power of minus 2 corresponds to which quantity? That unit represents pressure measured in pascals. Question 20. If force equals K times x to the power of n, and K has dimensions m⁰L to the power of minus 1, T to the power of minus 2, we can find n by matching the dimensions. Force has m⁰T to the power of minus 2, so we compare the powers of L. Minus 1 plus n must equal 1, which gives n equals 2. Question 21. What are the dimensions of pressure multiplied by volume? Pressure is mL to the power of minus 1, T to the power of minus 2, and volume is L cubed. Multiply them, and we get mL⁰T to the power of minus 2, the same as energy. Question 22. Which type of error occurs when an instrument isn't zeroed correctly? That's a systematic error, specifically called a zero error. Question 23. Why do we care about significant figures? Because they tell us how precise our measurements are, and they prevent us from pretending that our data is more accurate than it really is. Significant figures communicate the reliability of your results. Question 24. Why can't dimensional analysis give us numerical constants like pi or 1/2? Because dimensional analysis only looks at powers of quantities like mass, length, and time. Numbers like pi or 1/2 are dimensionless, they don't have units, so dimensional analysis can't tell you what those constants are. Finally, question 25. Let's check whether the equation S equals UT plus 1/2 AT squared is dimensionally correct. The first term, ut, has velocity times time that gives length. The second term, 1/2 t squared, is acceleration times time squared, which also gives length. Both sides have the same dimension of length, so the equation is dimensionally valid. And that's all 25 questions. If you followed along this far, you've got a solid grasp of physical quantities and measurements, an excellent foundation for all of physics. In the next video, we'll explore another topics of physics. Make sure to like the video, subscribe, and turn on notifications so you don't miss the next one. See you soon!